Swayam Prabha. Digital India. Educated India.
So, good morning everyone. Welcome to the first lecture of the last week, and I'm glad that you're still surviving. Okay. So, I'll start by briefing you about what the series of lectures this week that I'm gonna take will be about. And the theme of the algorithms is basically designing algorithms for NP-hard problems. I hope you all have been introduced to the notion of NP-hardness last week, and you all know that in all likelihood, or at least we all believe that we can't design polynomial time algorithms for NP-hard problems unless something happens which people don't believe to happen. And but the thing is, a lot of NP-hard problems are very useful in real life, and so people want to solve them anyway. So and they want to solve them efficiently, and the notion of efficiency in classical complexity is having an algorithm whose running time is polynomial in the size of the input. Okay. But because we can't have efficient algorithms for NP-hard problems, we come up with trade-offs. For example, one trade-off that you saw last week was a trade-off in the quality of the solution. So you said, okay, of course, if I ask you to give me an exact solution for an NP-hard problem, it's very unlikely that you can give that solution to me in polynomial time. But what if I want to get an approximate solution, a reasonably approximate solution? And last week you saw a lot of approximate algorithms for a lot of NP-hard problems, right? And of course, it's not true that all NP-hard problems exhibit nice approximation algorithms. A lot of NP-hard problems do not, and a lot of them do. But so this is one trade-off that people look at when they talk about NP-hardness. They try to compromise on the quality of the solution. There is another compromise that people usually tend to make is what you'll be seeing during the last 3 days of this week. Anita will be taking that. She'll be talking about randomized algorithms. Again, what are those algorithms? So when we try to design polynomial time algorithms for NP-hard problems, but when I say polynomial time algorithms for NP-hard problems, there has to be some trade-off, and the trade-off there is in the guarantee of the solution that you get, by which I mean the algorithm will run in polynomial time and it will output you some solution, but it might not output you the correct solution always. Okay. But then why are they used? They are used because the guarantee is that in most of the scenarios, it will output you the correct solution. In some scenarios, it might not. And this is a good enough trade-off for some people. For example, some people believe, or this is in fact true, that eventually we're going to run our algorithm on our systems. And no system is perfect. For example, there are always imperfections in the hardware on which you run the system. So in a way, there is always an error probability associated with the algorithm. Even if your algorithm was finding the correct solution always, the solution might be perturbed because of some imperfections in the hardware. And so software developers were like, okay, so if you anyway are allowing for such an error possibility from hardware side, why not as well allow for a slight error from the software side? And that error is really minuscule. So it will run for, when I say it will run for the algorithm gives you a good the exact solution in almost all scenarios, by which I mean the almost all scenarios could be as good as, say, it will give you the correct algorithm almost every time but once in 1 million. So that is a good deal for many problems. Okay. So I just want to make, I'm just trying to make a point that this is one of the trade-offs that people look at when they design NP-hard problems. Okay. So again, the goal of this series of lectures will be to design, let me say, good algorithms for NP-hard problems, and I'll describe what is the trade-off that we make when we design such good algorithms for NP-hard problems. But before revealing the exact framework, I'll reveal it slowly with the help of an example. Okay. And during that, I'll also tell you another framework which people use to cope up with NP-hardness. I'll come to it. So let me start by again stating the vertex cover problem. I hope all of you know it, but still I'll just state it for completion, because this is the problem that we'll be working with. Yeah, we'll be working with a lot of times. So in the vertex cover problem, one is given as input a graph G, and throughout the course of these lectures, we'll only be working with decision problems. And by decision problems, I mean the algorithm takes as input some things, and it always outputs either a yes or a no. That's all it's allowed to answer, output. So a decision version of a vertex cover problem is you're given as input a graph G and a positive integer k, and the algorithm outputs yes if there is a vertex cover of G of size at most k, and it outputs no otherwise. And again, what is a vertex cover of G? It is a set of vertices such that every edge of G has at least one endpoint in this set. Right. This is the vertex cover problem, which you all are familiar with. And you all have seen an NP hardness proof of this problem, right? Do you know of any polynomial time algorithm for vertex cover? When I say any polynomial time algorithm, of course I know it's NP hard, but say an algorithm that solves vertex cover for certain graphs, for example, in polynomial time. Have you seen any polynomial time algorithm for vertex cover? Yes. So you all have seen a polynomial time algorithm to solve vertex cover in bipartite graphs. So this is another paradigm which I wanted to talk about. This is not our paradigm, but this is another paradigm which people deal with, which is, this is an NP-hard problem. When we say it's an NP-hard problem, we know that on a general graph, we cannot expect to have a polynomial time algorithm for this problem, right? But for special graph classes, for special graphs which have a lot more structure than a general graph, we might have a polynomial time algorithm for such a problem, right? So this is another paradigm where people study these NP-hard problems on certain graph classes, certain restrictive graph classes. So bipartite graphs is one such problem, and you have seen that vertex cover is polynomial time solvable on bipartite graphs. Okay. So let's try to extend this idea and try to see, can we generalize this class of bipartite graphs? Like, can we generalize this class of bipartite graphs and get some polynomial time algorithms for vertex cover on those classes of graphs? Okay, and I'll tell you what I mean. What is this generalization that I'm talking about? So, okay, see, a natural question is, vertex cover is easy on bipartite graphs. What if you have a graph which is close to being bipartite? And when I say close to being bipartite, for example, suppose if you the graph is not bipartite by itself, but suppose if I delete one vertex from the graph becomes bipartite. Okay. So for example, let's say the graph G is such that it is almost bipartite. So these are independent sets. These are the across edges. They could be any sort of across edges. But there is a vertex V which makes it non-bipartite. But note that if I delete this vertex V, the resulting graph is bipartite. Okay. Suppose I want to solve vertex cover on this graph. Is it NP hard on this graph, or okay, what do you think? Should it be NP hard on this graph, or should it be polynomial time solvable? So this graph is almost bipartite. So if I delete V, I know there is the graph becomes bipartite. So let's see. Suppose I want to solve vertex cover on this graph, and for solving vertex cover, let us say guess we know there are two possibilities. Either this special vertex V will belong to a solution or will not belong to a solution, right? There are only these two cases that can happen. So we know if there is a vertex cover, if there is a vertex cover solution, if there is a vertex cover of size at most k, either V belongs to that vertex cover or V does not belong to that vertex cover. Okay. So suppose we can find an algorithm which solves which computes a vertex cover of this graph that contains V. That's one thing that we solve, and we also solve the problem where we want to get a vertex cover of this graph that doesn't contain V. Okay. Suppose we can solve both these problems. Then if you solve both these problems, can you say something about the vertex cover in G? Like in particular, what is our goal? Our goal is to find out, is there just a second, is there a vertex cover of size at most k in G? This is the question that we want to solve. Okay. So I'm saying, suppose I tell you that I give you a polynomial time algorithm. Suppose I give you a polynomial time algorithm for the following problems. For two problems I'll give you. One is, I'll tell you if there is a vertex cover in G of size at most k that contains V. And the second problem that I'll solve is there a vertex cover in G of size at most k that does not contain V. If I give you answers for these two problems, 1 and 2, then using these answers, can you get an answer for this problem? Okay, suppose the first algorithm, the answer for the first algorithm is yes. So it says that there is a vertex cover in G of size at most k that contains V. Then what should be the answer for this question? Question marked A. And if the second question says, is there a vertex cover in G of size at most k that does not contain V? If it says yes, then what should be the answer of this question? So if any of them says yes, the answer of this question should be yes. Okay. And if suppose both of them say no, then can G have a vertex cover of size at most k? Because as she pointed out, we have actually guessed whether we will go to the solution or not. If V goes to the solution, we try to see, is there a solution that contains V? And in the other guess, we have guessed that we will not go to the solution. In that case, we try to find out a solution without V. If there was actually a yes answer to the problem marked A, then one of these things should say yes, right? And if both of them are saying no, then actually there is no answer to the question marked A, right? So basically we have we know that we have come down to the case that if we can solve this question 1 and 2 efficiently, then we can solve question A efficiently, right? So it all boils down to solving these two questions. Let's see what we can do with these two questions. Let's try to design an algorithm for question 1 and question 2. Okay. Any ideas about going about it? Say question 1. So in question 1, we're trying to find a vertex cover of size at most k that definitely contains V. Exactly. Is this correct? So if we're looking for a solution that contains V, we might as well just delete V from the graph and instead look for a vertex cover in the remaining graph of size k minus 1, because we are picking V in the solution and now we want the remaining solution to be of size k minus 1, right? So this boils down to finding a k minus 1 size vertex cover in G minus V, right? Can you solve it efficiently? Can you solve this problem efficiently? Yes, because G minus V is a bipartite graph now. Right? Fine. So at least problem 1 we can solve efficiently. What about problem 2? But if I delete V, when you delete V, you also delete the edges incident on V, right? So how do you ensure that the vertex cover that you find in G minus V will take care of these edges that have been deleted? And this is probably the hint. So if you know that V is not going to be in the solution, what can you say about the neighbors of V? All of them should go, right? So in this case, what do we know? If V does not go to the solution, then we know that neighborhood of V should go to the solution. If you're finding a vertex cover without V, then all of its neighbors should be in the vertex cover, right? So neighborhood of vertex cover should go to the solution. Now what you can do? Sorry? Yes, so it's like the same thing. There, in the first thing, you knew that V goes to the solution. In that case, you could just remove V, decrease K by 1 because you've chosen V to be in the solution, and solve the problem on the remaining graph. In this case, you have chosen that N of V should go to the solution. So what should you do? You should find a vertex cover in which graph? Okay, let me just write it here. I made the space for this. So you want to find vertex cover in G minus neighborhood of V of size, right? And can you find such a vertex cover in G minus neighborhood of V? So G minus N of V is a bipartite graph now. Why? Because if G is bipartite, then even if I, if suppose a graph was bipartite, then even if I delete some vertices from it, it remains bipartite. So the only reason this G was not bipartite was because it had V. But now I have deleted all the neighborhood of V's. So in G minus neighborhood of V, V is an isolated vertex. So you can put it in any partition, right? You can, so even this question you can solve in polynomial time, right? So basically, you can solve vertex cover for such graphs in polynomial time. Such graphs meaning graphs that are, let me say, one distance away from being bipartite, by which I mean you can delete one vertex and make it bipartite, right? So, okay. The next obvious question is one special. Suppose I had two vertices here, so by which I mean if I delete two vertices, then I get a bipartite graph. So G looked like this. So there were two vertices, U and V. They could have an edge between them or they could not have an edge, and they have neighbors below. So this is two vertex away from being bipartite. So if you delete U and V, the resulting graph is bipartite. Now can you design a polynomial time algorithm for this problem? Again, note, what did we do in one case? We actually, as she pointed out, we guessed what the solution is going to pick from these conflicting vertices, like the vertices that are the reason for this graph not being bipartite. So we guessed if V should belong to the solution or not. If V belonged to the solution, we deleted V, right? And if V didn't belong, we knew all its neighbors would belong. And after doing these deletions, the resulting graph turned out to be bipartite and we could solve it in polynomial time, okay? Let's try to do the same thing. Even if there are two vertices, what we can do is, we can guess what subset of vertices will the solution pick from these two vertices. So the solution could either pick none of UV, or it could pick U, or it could pick V, or it could pick both U and V. We'll form 4 such questions, right? And in all the 4 questions, we'll try to see if it contains U, we know that we can delete U, right? And if it doesn't contain V, then it has to contain all its neighbors, then we can delete all its neighbors, and then you can observe that the resulting graph will still be bipartite and you can still solve the problem, okay? Anyway, we'll see the proof of it. So basically the point is, so the point is, one is not really special here. Even if you had 3 vertices here, or 4 vertices here, or 5 vertices here, we can design a polynomial time algorithm, and let us just see quickly what that will be. It's again along the same lines. So in general, suppose you have a set, in general, suppose you have a set X of vertices such that when you delete these vertices from the graph, the resulting graph is bipartite. Okay. So this set X could have size 2, 3, 4, any number that you wish to. I'm not restricting the size of X to be anything as of now. Okay. So this is how G looks like. There is a set of vertices which when you delete, the resulting graph becomes bipartite. So let's do this guessing business. So in this case, we create 2 power x many problems. In the previous, for example, in the previous situation, we created two problems. In this situation, we'll create too many x many problems. And what will these 2 power x many problems correspond to? Yes, each guess. So what is a guess? A guess is a subset of x. And that subset corresponds to the fact that I'm looking for a solution that picks exactly this subset from X and doesn't pick anything else. Okay, and because we are looking at all possible guesses, which will include the empty subset also and the whole of X also, we would have exhausted all possible scenarios in which a solution can participate with X. So basically what I'm saying is we'll create a lot of, just enumerate all subsets of X. So there'll be like phi, some x1, x2, so on, and x. So they are all the subsets of X. And for each such subset, so suppose let us call, so for any subsets, let's say X prime, we want to solve the following problem. We want to find a solution, vertex cover, of size at most k in G that picks X prime from X and does not pick X minus X prime from X. So basically we are looking for a solution that picks exactly X prime from X. Okay. So suppose we have solved this problem for each subset X prime of X. Then have we solved the problem for the original graph G? So the original problem is again, is there a vertex cover of size at most k in G? So what I've told you as of now, we'll see how to find an algorithm for this problem shortly. But as of now, suppose I tell you solutions for all these algorithms as in for every possible subset X prime of X, I told you a solution to this problem. Then do you know the solution to this problem? So again, suppose for one of these problems, so basically suppose there exists some subset X prime for which when we solve this problem, the output is a yes. The output is a yes. Then what can we say about this problem? Yes, because anyway this problem is giving me some vertex cover of the graph, and then you can just give me this vertex cover. Now suppose for no X prime, suppose for every X prime this algorithm says no, then can there be a vertex cover in G of size at most k? Or in other words, we can put the problem in the contrapositive way, in the sense that suppose there is a vertex cover of size at most k in G, then can it happen that for every X prime your answer is a no here? Yeah. If G indeed had a vertex cover of size at most k, then look at its vertex cover. Okay, and look at this vertex cover and see what vertices this vertex cover picks from X. Suppose it picks some vertices from X. I mean, it could pick or it could not pick. If it doesn't pick anything from X, then look at this case when X prime was this phi. Then for this X prime, this algorithm should have outputted yes, right? Because if this X, if a vertex cover here was not picking if it was not picking anything from X, then that means it's picking phi from X. So what is this problem saying? This problem is saying that when X prime is equal to phi, this problem is saying that you're trying to find a vertex cover that picks phi from X and does not pick X from X. So it's basically saying it is not picking anything from X. Then this problem should have said yes, right? So basically that means if it has a vertex cover of size at most k, it has to pick something from X, at least as of now. So suppose it picks something from X. Okay. Now let us call this subset let's say X double prime. So X double prime would have been enumerated. So look at the subset X double prime. It would have been enumerated in this list somewhere because it's a subset of X. Right? Now look at this Look at when you were solving this problem for X prime is equal to X double prime. What were you solving here? You're looking for a vertex cover that picks X double prime and doesn't pick anything else. So why would this solution that you have for G right now, why would that not be a solution for this problem? So basically if there is a vertex cover here that was picking X double prime from here, and it was exactly picking x double prime from x, then when you look at this problem for x double prime, this would say yes. So it can't happen that there is a vertex cover here and you said no in all these things, right? So again, we have boiled down to solving a problem in G to solving 2 power x many problems in like too many x many some sort of problems, right? Now let us see if we can solve this problem efficiently. So what is this problem? We are looking for a vertex cover that picks exactly some fixed subset x prime from x and doesn't pick anything else. Okay. So now the task is to solve this problem. Any ideas? Like this, the idea is the same as we saw in the previous case when x was a single vertex. Exactly. So this problem is asking for a vertex cover that picks x prime. So if you're looking for a vertex cover that picks x prime, you might as well take x prime and delete it from the graph. And in this graph, then what are you looking for? You're looking for a vertex cover in G minus x prime of size k minus x prime, right? Okay. Is this a bipartite graph now? Because if it was a bipartite graph, then we would have done the same thing. We would have looked at a polynomial time. We would have solved it using the polynomial time algorithm for bipartite graphs. But is it a bipartite graph as of now? No. So okay, but we know that we are also looking for a solution that does not pick anything from x minus x prime, right? So we can do the same thing. We have picked x prime and we know we are not going to pick x minus x prime. So now we can delete all the neighbors of x prime. So if we are not picking anything from x prime, then we have to pick all the whole neighborhood of x prime, right? So you have to pick all neighbors of x prime. So basically, sorry, not x prime, but x minus x prime, right? Okay, so then like let me call this graph as some g star. Let me call this k as k star. So firstly, we can delete x prime and decrease k by k prime, and then when we pick all neighbors of x minus x prime from this g star, we can delete these neighbors and we can decrease k star by again the neighborhood of x minus x prime, right? So basically, what is this graph that we have now? In this graph, we have deleted the whole of x prime and we have deleted all the neighbors of x minus x prime. Is this a bipartite graph now? Why? But I have not deleted x from the graph. I have deleted x prime from the graph and I have deleted all the neighbors of x minus x prime. So basically x minus x prime, so basically this part, this is x minus x prime is still in the graph, right?
But the edges of x minus x prime are being covered.
Yeah, but what about the edges that are inside the vertices of x and x prime? This is a set of vertices now in the graph. When there was a single vertex, we didn't have to care about all these things. It was just a single vertex, but now we do have to. And to resolve this issue, just focus on the definition of the problem that we're trying to solve. We're trying to find a vertex cover that picks exactly x prime from the graph. So if suppose after deleting x prime in x minus x prime there was some edge, then can you find a vertex cover in this graph that picks exactly x prime from x? So suppose the answer for this problem, suppose it was yes. Okay, then suppose the answer for this problem was this. That means there was a vertex cover in this graph that picked exactly x prime and didn't pick anything. If it didn't pick the remaining x minus x prime thing, and if there was an edge between two vertices of x minus x prime, then any vertex cover has to pick one of these endpoints, right? So any vertex cover has to pick something from x minus x prime, and hence then this problem cannot have a yes answer. So basically you delete x prime and you look at x minus x prime. If it has an edge, then you just say no to this problem because it cannot have a solution which picks exactly x prime from G, from x. Okay, I'll just repeat it once again. So the point was, what have we done here is, we said we are looking for a vertex cover that picks exactly x prime from x. We said, okay, in that case, delete x prime from the graph and decrease k by k prime. Okay. Now we said that, okay, after doing that, because we are not going to pick x minus x prime, we know that all its neighbors have to go to the solution. So we deleted all its neighbors and decreased k star by this. Okay. But note that basically I should be more careful and say that these are the neighbors of x minus x prime in G minus x, right? I mean, there could be neighbors of x minus x prime in x itself. There could be neighbors of vertices here amongst themselves also. But we are not deleting them because we can't delete them, because we are not looking for because we are looking for a solution that does not pick anything from x prime minus x prime, right? So now we said that, okay, we have deleted x prime from the graph and we have deleted the neighbors of x minus x prime from this graph. Okay. And of course, if x minus x prime was an independent set, then we get a bipartite graph because we've deleted all its neighbors down there, right? And if this was not an independent set, then we can clearly say that there is no vertex cover in G which picks exactly x prime from x, right? So that's the idea. So using this again, so basically we have seen an algorithm to solve this problem also, and that's a polynomial time algorithm again, right? So to basically get an algorithm for this problem, how much time have we spent? So basically we created 2 power x instances, say, and we could solve each instance in polynomial time, right? So basically we have got an algorithm for vertex cover that runs in time 2 power x into, let me just say, polynomial in n, right? Now, okay, so this was modulo that I have given you some x, right? So if suppose in a graph I give you a set of vertices whose deletion makes the graph bipartite, then you can, in those kind of graphs, you can solve the problem in 2 power x into polynomial in n time, right? And the point to note here is that if suppose there are graphs where there is a small set of vertices whose deletion makes the graph bipartite, small meaning any constant, fix any constant of your choice, 1, 2, 3, 4, 5, 6, 100, any constant, because this is a constant, 2 power, that constant will again be a constant. So asymptotically this will be a polynomial time as long as you give me an x of constant size, asymptotically speaking. Of course, as you grow the size of x, this function is growing, but if you treat that as a constant, if you know that, okay, I'm always going to give you graphs, in all the graphs that I'm going to give you, I can always give you x of size, say 10. Then this 10 becomes fixed. Then I know this is nothing but 2 power 10, just some constant, and then it's a polynomial time algorithm, right? So basically, now I can talk about what is the framework that we'll be dealing with. See, we have designed an algorithm for an NP-hard problem whose running time is polynomial in the input, but of course it is exponential in something else. That something else here being the number of vertices which you need to delete to get to a bipartite graph, right? In some sense, here we are doing a multivariate analysis of the running time of the algorithm. What do I mean by that? So normally the kind of algorithms that you've seen so far, when you have to compute its running time, you always try to compute it as a function of n alone, right? And hence, whenever you say there's an NP-hard problem and we can't solve it in polynomial time, you mean you can't find an algorithm which runs in time that is polynomial in the size of input, but but the running time analysis is solely in the input size, right? So here what we have done is, we have tried to design an algorithm for which we can guarantee that, see, it will run in polynomial time until a certain, let me call this a parameter, unless a certain parameter is a constant. So in some way we have pointed out that, see, this is what is making the problem hard. So for instances of vertex cover where x had small size, those instances were actually polynomial time solvable, right? So we're doing this multivariate analysis, as in it's polynomial in the input size, but it could depend exponentially in some other parameter. Okay? And what we have actually done here is we've actually exploited the structure of the graph. So like we know that when we delete x, the resulting graph is a bipartite graph, and we tried to exploit the structure of this bipartite graph to get such an algorithm, right? One important point to note here is that, as I said before, people have been trying to exploit the structure of the graph to get polynomial time algorithms. For example, this vertex cover example on bipartite graphs, people exploited the structure of bipartite graphs to get a polynomial time algorithm for vertex cover. One point to note there is that algorithm will only work if the input graph is a bipartite graph, right? If to that algorithm I give as input any other graph, it will not work. Like you don't know what steps to execute, because the steps there are very particular to the fact that the input graph is a bipartite graph, right? But note that this algorithm, the guarantee is that this algorithm will work well if this x has small size. But even if I give you a set x of arbitrarily large size, this algorithm will still work, right? I mean, it will give you a very bad running time, agreed. But this is an algorithm that will work for any graph. And for example, can you always find a set x of vertices in a graph, no matter of what size, such that its deletion makes the graph bipartite? Yes, just take any n minus 2 vertices. So g minus x will have 2 vertices, so either there is an edge or not an edge. So in either case, the resulting graph is a bipartite graph. So you can always find a set x like this, right? And so this basically, the point here to note is that this algorithm works for all graphs, unlike algorithms which exploit the structure of the graph but then only work for those kind of graphs. So this algorithm works for all graphs. The good thing here is that it works in polynomial time for graphs which have small x, right? So this is the theme of the algorithms that we are going to study in this series of lectures. These are called parameterized algorithms, in the sense that with a problem we associate a parameter. For example, we will see what I'm saying, but for example in this problem we associated x as a parameter. So x is a parameter, meaning we associated the parameter in this problem was the size of say the size of the smallest set whose deletion makes the graph bipartite. Okay, so if that is the parameter, so x was that parameter, we have designed an algorithm whose dependence on the parameter could be anything. Okay, it could be 2 power x, it could be 2 power x, it could be any function of x, I don't care, at least theoretically we don't care, but it is absolutely polynomial in the size of the input. So for problems which have a fixed, so for instances which have a fixed parameter value, this function, no matter how bad it is, at least theoretically this will always be a constant if x was a constant. Okay, so theoretically this is a polynomial time algorithm for such problems where x is a constant. So of course, if we have good functions here, like here we have a 2 power x function, so it is indeed a good algorithm when x values are reasonably small, right? So we are going to study these kind of algorithms in the course of next lectures throughout the week. So here, while we are here, let me just point out one more thing. So here, for example, the parameter that we chose was was x, and x had nothing to do with the vertex cover of the graph. X was a set of vertices which made the graph bipartite, right? But for example, one natural question is, we know that this algorithm will work well for graphs where x is small, where you have a small set of vertices whose deletion makes the graph bipartite. Okay. By the way, this problem is called odd cycle transversal, which is given a graph G and an integer k. You want to delete k vertices whose deletion makes the graph bipartite.